This video will show you how to carry out multiple linear regression in SPSS. It uses the dataset VO2 dataset full. The population from which the sample was taken was males and females aged between 20 and 40 and weighing between 135 and 220 pounds. The research question we want to answer is, to what extent can we predict absolute VO2 max from weight, age, gender, 1 mile walk time, heart rate, body temperature and height on the given population? To answer this question, we'll create a linear regression model from a sample of data taken from the whole population, who we want to predict VO2 max for. We do not know what the equation of the model will be for the population, but we can make estimates based on our sample and use this to make predictions on the whole population. Before we can create a multiple linear regression model, we need to check that there is a linear relationship between each independent variable and VO2 max. We also want to check that the independent variables do not have multi-collinearity. To do this, click Graphs, Legacy Dialogues, Scatter/Dot and choose a matrix scatter. Add all the variables to matrix variables. In titles, you should add an appropriate title. In options, we can define how to deal with missing data, but this does not apply to us. Click OK and we get the following output. Double-click to activate the chart editor to make this bigger. Go into Edit and Properties to resize it. First, we want to look at the relationship between each independent variable and VO2 max. Weight and 1 mile walk time and gender seem to have the strongest relationships. We also note that height and weight have a very strong positive relationship, which suggests a problem of multi-collinearity. We also want to look at the correlation matrix. To do this, click Analyze, Correlate and Bivariate. Again, add all the variables to the variable list. We will use Pearson's correlation coefficient with a two-tailed test of significance. Again, in options, we can define how to deal with missing data and include any optional statistics. Clicking OK, we get the correlations table. The values in the table back up our comments on the correlation matrix. 1 mile walk time has the highest correlation with VO2 max. Gender also has a high correlation. Weight and height have a medium strength correlation, and then age, heart rate and body temperature have a very low strength correlation with VO2 max. Height and weight are shown to have very high correlation, as we expected. Since some variables have low correlation and we have some multi-collinearity, we may want to remove some variables from the model if they're not significant predictors. But to begin with, we will consider a linear regression model with all the independent variables included. To do this, click Analyze, Regression and Linear. Add VO2 max as the dependent variable and add all the other variables as the independents. We will use the enter method as we want SPSS to include all the variables. We do not have a selection variable, case labels or WLS weight. In statistics, we want to include the part and partial correlations. In plots, we want to include a histogram and a scatter with the standardized predicted values on the x-axis and the standardized residuals on the y-axis. We will use the graphs to test the assumptions of linear regression in video 3. Click OK to get the linear regression output. First, we have the model summary. We are interested in the R-squared value and the standard error of the estimate. The R-squared value is the coefficient of determination and represents the amount of variation in VO2 max that can be explained by changes in the independent variables. The adjusted R-squared value only accounts for significant predictors. The R-squared value would increase if we added more predictors, even if they do not improve the model. The standard error of the estimate tells us how much the observed values for VO2 max differ from the values from the regression model. We have a standard error of the estimate of 0.0971292. This is small, so suggests that the linear regression model is a good fit. However, the range of VO2 max values in the dataset is only 3.2356, so we would not be expecting a large value for the standard error, as even a badly fitting model would lie close to the observed data points due to the small data range. Next, we have the ANOVA table. This tests the null hypothesis that all the coefficients are zero and we can predict VO2 max from the mean. The alternative hypothesis is that at least one of the coefficients is different from zero. We're interested in the p-value, which is given in the last column. Since this is less than 0.05, we can reject the null hypothesis at the 95% significance level. Now we have the coefficients table. This gives the estimates for the coefficients of the regression model based on our sample. The multiple linear regression equation is VO2 equals 10.006 plus 0.008 times weight minus 0.027 times age plus 0.933 times gender minus 0.217 times time minus 0.014 times heart rate minus 0.049 times temperature and minus 0.001 times height. We also have significance values for each predictor. Here, a t-test is used to test the null hypothesis that the true population value of the coefficient is equal to zero. The alternative hypothesis is that it is different from zero. For body temperature and height, the p-values are greater than 0.05, so we cannot reject the null hypothesis. This means we should consider removing these predictors from the model. In summary, first, we looked at how to check that there is a linear relationship between the dependent and independent variables. We also looked at the relationship between the independent variables to check for multicollinearity and found that this may be a problem with height and weight. Next, we looked at creating a linear regression model and discussed the appropriate options to get the output that will help us make decisions about the model and check the assumptions of linear regression. Then, we looked at the SPS output. First, we had the model summary given the R-squared value, which gives the percentage of variability in the VO2 max due to changes in the independent variables. We also have the standard error of the estimate, which tells us how much the observed values for VO2 max differ from the values predicted by the regression model. We also have the ANOVA table, which tests the null hypothesis that a mean model is a better predictor of VO2 max than our regression model. Since the p-value was less than 0.05, we can reject our null hypothesis in favour of the alternative hypothesis that our regression model is better. Finally, we use the coefficients table to get the equation of our linear regression model. Video 2 will cover variable selection methods to remove insignificant predictors, and video 3 will cover interpreting the model and checking the assumptions of linear regression.